Hello everyone. My name is Sayali Tope. I'm from University of Utah in United States. The title of my census latest paper is Development of a sub-10 ppm limit of detection lateral nanogap gas sensor. The main focus of this work is fabricating a lateral nanogap which can be used to increase the nanogap area, and because of that we can lower the detection limit, detection threshold of the chemical we are sensing further down to sub 10 ppm levels. There is a huge demand for sub 10 ppm hexanal detection. So hexanal is a biomarker for lung cancer, for chronic obstructive pulmonary disease, for indoor pollution, then also for food quality and spoilage. So there are various applications in agriculture, safety, food quality, healthcare, which require sub 10 ppm hexanal detection. So our research group previously we designed a nanogap gas sensor. So nanogap sensor is basically two electrodes which are separated by a sub 10 nanometer nanogap, and this is a molecular bridge based sensor, meaning that when in the presence of the target molecule, a molecular bridge is formed between the two electrodes, and the current starts to flow, increasing the current exponentially, and that is triggering the detection. So this sensor, we particularly used it for hexanal detection. So the hexanal was chosen because hexanal is a biotic stress VOC in sorghum plants. Sorghum is a biofuel crop, and in United States, the size of the farms is huge. And by the time the farmers know about the potential damage, 30% of the yield is lost. And that is equivalent to $36 billion of biofuel. And now the fossil fuel sources are depleting. We are more and more leaning towards biofuels. So to increase the yield of the hexanal, to increase the yield of the sorghum by detecting this hexanal, we developed this sensor which can send a signal to the mobile phone, and actions can be taken early. But the problem with this horizontal nanogap structure is the limit of detection of this sensor is limited to 33 ppm of hexanal. So from our initial testing, we have seen that as the nanogap area increases, the limit of detection goes down, but our failure rate also increases. So the problem is when we want to get higher area, we have to etch the anchor furthermore to increase the overlap area. And that makes the nanogap very unstable. The top electrode is like a cantilever membrane, and because of slight vibrations or probing forces, the stiction forces, it just shorts and the devices fail. So with that horizontal structure, we were not able to create nanogaps which are higher than 62.5 micrometer square area. So to solve that, we came up with the lateral nanogap structure. So in the lateral nanogap, the two electrodes are firmly attached to the substrate. So there is no cantilever or the moving parts. And the main principle of how it lowers the VOC is shown over there. So because of the higher area, more and more molecular bridges can be formed for the same concentration of the gas. And because of more bridges, the on current increases, but the off current relatively stays the same. So for the same concentration of the gas, we get the higher on-off ratio. And that way we can lower the limit of detection. So this is the process flow I designed for developing this nanogap. So this is pretty simple flow. The patterning of the first electrode, then a sacrificial layer using atomic layer deposition is used to create a 5.2 nanometer gap, and then depositing second electrode, and then etching the sacrificial layer to release the nanogaps. But the main important thing in this, the problem I faced was while depositing the sacrificial ALD layer. So we all know that ALD is angstrom scale precise, um, and it can deposit a very good uniform layer, but it fails in the conformality in the sub-10 nanometer regions, and that is especially on the 3D structures. So it can deposit the layers very well on the top, but when it comes to depositing layers on the side walls, it lacks the conformality, and because of that, there is no deposition on the side wall. The two electrodes, they short, and they cause the fabrication level failure. So to solve that, I calibrated a rarely used exposure mode ALD. So in the exposure mode, when the precursors are flown in the process chamber, the dosing and the purging cycles are separated, so there is no overlaps. And for the dosing cycle, the purge valve is closed, so all the precursor stays inside the chamber for a really long time, and it coats all the surfaces evenly. And as we can see in the SEM, we got a really conformal layer, and I was able to increase the conformality from 0% in the normal mode to 80.39% in this exposure mode. So this special method is used to deposit the sacrificial layer, which later makes the nanogap. Here are some pictures of the fabricated sample. So this entire process is a wafer level fabrication process, and I was able to get areas from 100 micrometer square to 1000 micrometer square. And here is a quick video of the testing method. So in the gas chamber, I have 1000 micrometer square device, and 2.5 ppm hexanal sample was created in a big Tedlar bag. Using the purple pump, the sample is flown into the chamber, and all the data is recorded using the Keithley parameter analyzer. So this is a graph of resistance versus time. So when the hexanal is exposed on the sensor, the resistance drops and it settles at certain value. So this is what we call detection. And when we start purging the hexanal, the sensor resistance goes back to its original value and the sensor recovers. So this change between the on resistance and off resistance is uh, is the um, is the indication of a successful detection. Here are these same plots we got from Keithley, and here instead of resistance, we are showing them as a current. And for example, for 700 micrometer square area, we got a off current of 305 nanoampere. And when we started the hexanal exposure, the current started increasing and it reached to 460 nanoampere as on current. And when we started purging it, it again went back to its original value and gave us the on-off ratio of 1.51. So before, with the horizontal nanogap, because we cannot increase the nanogap area, there was no capability to detect sub 33 ppm of hexanal. But now we got the lateral nanogap structure. With that, we were able to detect down to 2.5 ppm. So the nanogap area was increased by 16 times, while the LOD is lowered by 13 times. And here is an example how the lowest concentration is found. So for example, for that 700 micrometer square area, first we define the noise floor. The noise floor is just flowing the nitrogen on the sensor and measure the fluctuations of the sensors. And if the hexanal response is higher than the noise floor, then it is called a true detection. So for 2.5 ppm, for that 700 micrometer square sensor, the response was falling below the noise floor. So that was no detection. And that way, the lowest detectable amount was 5 ppm. So that way, all the lower amounts are measured for these nanogap areas. So in the conclusion, a stable conformal lateral nanogap device with the area of 1000 micrometer square and a 5.2 nanometer nanogap was achieved, and with a capacity to fabricate even larger nanogap areas. These are just some examples I have created. And in this research work, we proved that increasing the nanogap area can lower the limit of the detection of the nanogap gas sensors. And I would like to thank our sponsors for this, the ARPA-E Department of Energy. Because of their funding, we were able to complete this research, and all the fabrication is done in Utah NanoFab, and with the state-of-the-art facilities over there. Thank you.